what we're going to do now is we're going to slightly switch gears to another model of conceptual knowledge, another model of how our knowledge is represented in our mind. And we're going to talk about, it's very related, but we're going to talk about connectionist networks. So it's super related to the idea of Collins and Loftus's spreading activation model. And it really is something, this idea has been very important in understanding how our mind works, but I would say probably even more important in actually designing and creating alternatively intelligent or artificial intelligence machines. So just to kind of show you the leaps that occurred as we've been able to improve our connectionist networks, I'm going to show you this video of a self-driving car from 1986. Okay, so this was at the beginning of self-driving technology. This is a self-driving car at the beginning of around 1986. So let's take a look at how good self-driving cars were back then when they were first being developed. All right, so in case you're wondering, the video is playing. That is the speed that that self-driving car is able to maneuver at. The gear in that self-driving car is why it's a van rather than a little car. And basically, if it had a connectionist network, it had a very limited connectionist network. Oh, look at it go now. It had a very limited connectionist network, and the behavior of that car was very limited as well. Compare that to what we have today, where we have cars like the self-driving Teslas that can actually drive and maneuver and turn. And you can see that the steering wheel is not being touched by the hands, maneuver to where it needs to go, stop when it needs to stop, make left-hand turns, not crash into things. And it is doing it all at a very, very quick speed. We're going to see the architecture of what underlies that particular ability. We're also going to take a look at the same architecture that underlies large language models like ChatGPT. So the fact that you can ask ChatGPT a question like, how do you use connectionist architecture to do the things that you do? And it will come up with an answer that is rational, that is convincing, that is consistent. Again, that is going to, we're going to see the underlying framework that is allowing things like that to occur. And then the last thing that I want to show is just how far this ability has come. And what I did is Sora is part of the ChatGPT network of AI assistants. And I put in a prompt for a psychology professor whose name is Paladin Sane and who is heavily inspired by David Bowie. And this is the video that it came up with. So apparently I still have room to increase my David Bowie-esqueness in this. But again, this is massively convincing. This is very, very realistic. In fact, you have to start doing that search, that serial processing search, really, to see the things that don't make any sense. So the flaccidogalagy, I don't think is a branch of psychology that I'm aware of. But basically, the abilities that we now have to implement intelligence comes from this idea of these connectionist networks, these connectionist architectures that underlie these programs. So we have come across connectionist networks a few times in this course already. So if you remember when we took a look early on about how our letters recognized, the template model, not a connectionist network model, but the pandemonium model was. So that architecture proposed in 1959, they didn't have, I don't believe, the ability to implement it at the time. But this is basically the same idea that we're going to see today that is present in a connectionist architecture. So we're going to talk again about knowledge representation, and then we're going to take a look at connectionist networks. and how they can implement that knowledge representation. How do they actually work, and what might they tell us about the way that our minds actually work? All right, so let's take a look at knowledge representation. So consider the exclusive disjunction X or Y, right? So the exclusive conjunction X or Y. So for example, you must participate in research or write an essay to earn course credit, but you can't do both. So we can understand what this means. We can understand that if you have this on a syllabus, you know that, okay, to earn course credit, I'm going to participate in research or I'm going to write an essay. But if I do both, I can't earn the course credit. But if I do neither, I won't earn course credit either. So in this case, we have an X or Y proposition where the X is participate in research, the Y is write an essay. So the fact that we can figure this out means that it's represented in our mind somehow. So how might this be represented in our mind? Well, one possibility, and this is not a connectionist network, but this is like a list representation or a proposition representation. So if you wanted to solve this exclusive disjunction, you could simply have a list of the 4 cases that are possible. So if you have no X and you have no Y, false, which means you are not participating in research or writing an essay, so you don't get the course credit. If you have X, but you don't have Y, then it's true. You are participating in research, you get the course credit. If you do Y, but you don't do X, that's also true. You are writing an essay. However, if you do X and you do Y, it's false. So you're doing both, and that's explicitly not allowed. You can't do both. So it could be that the way that we solve these types of problems is we just have that list. If no X and no Y, then it's false. If Y alone, then it's true. If X and Y, then it's false. And that's the way that we solve these problems. But how could we maybe represent this in our mind a little bit differently? How might we be able to represent this same piece of knowledge and come to the same conclusions, but in a different type of representation? And that's what we're going to take a look at with connectionist networks. So a connectionist network, this is another model of how our knowledge is represented. It's a parallel distributed processing model, or a PDP model. And what it is it's made up of units and it's made up of connections. And these parallel distributed processing models, these connectionist networks, are what allows self-driving cars to operate. It's what allows things like ChatGPT, these large language models, to do the amazing things that they do. It's what allows AI programs like Sora to come up with videos based on prompts. So we're not going to delve too deep into explaining how those achievements are done. We're going to go as deep as we can into number recognition. So if you see an image like this, how can you tell that that is the number 7, even though it's a very degraded image? And that's where we're going to kind of camp out with our connectionist network. So we already kind of saw this and talked about it when we were talking about how our letters recognized. But now let's turn our attention to how numbers might be recognized. And this example comes from a video, and we'll watch a little bit of it later on, from 3 Blue, 1 Brown YouTube channel. And basically they showed how a connectionist program, a connectionist architecture, could be used to recognize numbers. So they started off with a number like this. So this would be the input. And everything that is in that blue circle, that is what gets input to the system. And what is the system? Well, the system looks like this. So this is a connectionist network. And you can understand why it's called connectionist, because there's about 8 bajillion connections in this particular network. This is also one of the reasons why when Selfridge proposed his pandemonium model back in 1959, nobody built it, because the computational processing that would have been required would just have been astronomical. Now we have the ability to do that, and we end up with models that look like this. So what is this model? Let's break it down. Let's get the pieces of this model going. So first off, in this connectionist network, it's made up of units and it's made up of connections. So we have units and connections, and the units, they are split into three different groups. So we have input units, and these are the units that are activated by stimuli. So in this model here, the input units are the ones on the left. And in this particular model, there are 784 input units. And the reason that there are 784 input units is because the image that is input into this model is an image that is 28 pixels by 28 pixels. So if you remember looking at that number 7, it was very pixelated. It's because that image is 28 pixels tall by 28 pixels wide. So each of those circles is a pixel in that image. So that top circle is pixel row 1, column 1. That second circle from the top, pixel row 1, column 2. That third pixel, pixel row 1, column 3. All the way down to the bottom one, pixel row 28, column 28. We have all 784 pixels are being input. So if it's a black pixel, the input is 0. If it's a white pixel, the input is 1. If it's different shades of gray, it would be wherever that falls on the 0 to 1 spectrum. All right, so we have the input layer. That's where the information goes in. We then also have the output units, and those are in the output layer. And those are the ones that communicate the information. So the output layer is that layer right there that has the output units. And basically, that is where you read what the system has decided. So in this case, you would take a look at the output 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, and you would look at which one is activated the most. So in this case, 5 is activated the most. So the decision that this connectionist network is making is that the input that it just received was the number 5. Incidentally, if you remember from really early in this course, this is a physical symbol system as well. And the output units are related to the outside world by interpretation. So we are able to look at that and say, oh, 5 is the one with the highest activation. You must be looking at a 5. And the input units, they are the ones that are related to the world through designation, where we tell them this pixel is on, this pixel is off, this pixel is gray, this pixel is black. So we have the input units in the input layer. We have the output units in the output layer. The magic occurs, and I almost literally mean magic. The magic occurs in the hidden units. And the hidden units are the ones that process the information. So the hidden units are the ones that you don't typically see unless they're represented here and visually. And these are the hidden units right here. So that's one layer of hidden units. That's a second layer of hidden units. And these are the ones where the processing of the information occurs. These are the units where the cognition in this system actually occurs. So we have these hidden units. They're between the input and the output units. They do the work of processing the information. And then finally, we got connections between the units. And very importantly, these connections are differently weighted. And that's also where that magic occurs. So you can see here, there are different connections here, and there are different colors, and there are different widths to those colors. So if I remember the coding of this correctly, the blue connections, they're excitatory connections. They are connections where a blue link makes whatever node it's connected to more active when it sends its signal. The red links, whatever they're connected to, that node becomes less active when it gets a signal from a red connection. And then the thickness of the connections are the strengths of the connection between those two nodes. So we have all these connections between the input layer and layer 1 of the hidden nodes. We have a bunch of connections between layer 1 and layer 2 of the hidden nodes. And then we have connections between layer 2 of the hidden nodes and your output units. And that is the entire architecture of this particular connectionist network. All right, so that's the architecture of the connectionist network. So how might this be made, or how might it be possible to represent your knowledge in something that looks like this? How could this potentially represent your cognition, your knowledge, in terms of what we are able to do and what we are able to know? So let's go back to this example here of the exclusive disjunction. So how can this be represented differently in your mind? How can this be represented with a connectionist network? Now, I chose this one because this is one that can actually be represented with a very simple connectionist network that we can all follow along and say, okay, yeah, I can see how that works. That makes sense. The more complex that you get, the less you know what is actually going on in your network. So that is one of the real drawbacks in terms of connectionist networks, is the idea that we can do many wonderful things like letter recognition, self-driving cars, large language models, but we are not exactly sure how it's doing that. We know how to build it, but really we don't know what we just built. So I'm going to show you an example where we can actually understand what we built. And it is a connectionist network that is designed to solve the problem. You must participate in research or write an essay to do course credit, but you can't do both. Solve the problem of X or Y when you can only have X, or you can only have Y, but you can't have both. All right, so we got an input layer for this problem. And that input layer has two nodes. And the node is either whether you got an X or whether you got a Y. So that's where we input the information into this connectionist network. We then have a bunch of hidden nodes, and we got two layers of hidden nodes. And then we have our output layer, and the output layer simply indicates whether the statement is true or whether the statement is false. So again, if you choose X only, it would be true. If you choose Y only, it would be true. If you choose neither, it would be false. If you choose X and Y, not allowed to do that, it would also be false. So we're almost there with our connectionist network. We just need to make some connections. So those are the connections there. And some of those connections are excitatory connections. They have positive weights associated with them. And those are those connections right there. And then other connections, they have negative strengths with them. They are inhibitory connections. And we have those connections right there. So we're going to give them dotted lines so that we know that they are inhibitory. And then the last thing that I'm going to mention that I failed to mention is that the numbers inside the hidden layers, that is how much of a signal that node needs before it fires. So if the node in the hidden layer has a 1 connected to it, as long as it gets a strength of 1 activation being sent to it, it'll activate. For the one that has a 2 in there, it needs a level 2 activation in order for it to then activate and send its signal down the connectionist network. And the last thing that we need to do is we need to set the default output for this connectionist network, and the default output is false. So we are now ready with our connectionist network to see how this representation would actually solve the X or Y exclusive disjunction problem. So let's see what happens when you have X. So let's suppose that you have X, and we know that the conclusion to that should be true. So will this connectionist network give us that output? Will it change its output from false to true? So again, remember, we're starting with a default of false. So now we input X, so that X node gets activated. Once it gets activated, it sends its signal down to whatever it's connected to at the weight of those connections. So it sends a signal of 1 down to that first layer of that hidden nodes, and then it sends an activation of 1 as well. 1 is not enough to activate that number 2 node because it requires 2 units of activation. So that hidden node cannot get activated. But 1 is enough to activate that top node. So that node gets activated. Once it gets activated, it sends its signal down to whatever node it's connected to at a strength of 1. That strength of 1 is enough to activate that hidden node that it's connected to. And now this node is going to fire off its connections, and it has a strength of 1 that is being sent to the true node. And importantly, it has a strength of -1 that is being sent to the false node. So not only does it turn on the true node, but it also then turns off the false node. And we get to our conclusion that yes, it is true. If you just have X, you've done it correctly. That is a true conclusion. So we have solved this problem. The network came to the correct solution. What about when we just have Y? Well, when we just have Y, the conclusion should be true. So let's see if that happens. So once again, now we start with the default network when there's no activation and we have false activated by default. In this case, Y is activated, sends its signals down from that input layer at the strength of its activation. So that link, not enough to turn on the node in the hidden layer that it's connected to. This connection, though, is strong enough to turn on that hidden node, and then that hidden node fires its weight to this hidden node, and it's able to turn it on because of the weight that was associated with that connection. So once again, that node then sends its signal of 1 to the output layer of true, turning that on. And it also sends its signal of -1, turning off the false node. And once again, we have the conclusion that if you just have Y, conclusion is true. And in this case, the network, once again, correctly reasoned through this exclusive disjunction. All right, suppose you have X and Y. So in this case, you have X and Y not allowed. You can't do both. So will this network come to a conclusion that this is false? Will this network say, no, 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 this is not true. This is actually false in this case. Well, let's see what occurs. We have X, so the X node gets activated in the input layer. We have Y, so the Y node gets activated in the input layer. X starts sending its activation to the hidden layer. So we got a strength of 1 activating that node right there. We have a strength of 1 being sent to the hidden layer, not quite activating that node right there, but now that activation is up to a 1. It needs an activation of 2 before it fires, but now we've gotten it halfway there. However, now that Y input layer also sends an activation of 1 to that node. Now finally it turns on. The Y also sends an activation of 1 to this bottom node over here. So now let's start back at that top node in the hidden layer. Activated, sends its activation down to the next node that it's connected to. That bottom node activated sends its connection down to the node that it's connected to. So now that node has an activation of 2, more than it needs to fire. However, that center node now sends its activation. It's an inhibitory activation of -2. So we have +1 from the top node, +1 from the bottom node going up to an activation of 2, and then -2 from that center node, bringing us back to an activation of 0. That final hidden node now will not fire, and our model returns an output of false, and that is correct. You cannot have X and Y. And now to kind of finish just the analysis, suppose you have no X and you have no Y. Well, then the input layers are never activated. No activation is sent to any of the hidden layers. No nodes are fired. And then we end up with the default situation of this network, which is false. So if you don't have X and you don't have Y, the conclusion this network will give is that it is false and the network is correct. So this is a very simple connectionist network that basically has all the ideas that are in a Tesla to help it self-drive, that are in ChatGPT to help it write essays. And you can see how this list of representations can be differently represented in your mind with a connectionist network as simple as this. So as simple as 2 inputs, 2 outputs, 2 hidden layers, 4 hidden nodes in total, that can implement in our minds or represent in our minds how we understand and how we deal with that exclusive disjunction. All right, so we're going to end today at this point. Next time, we're going to take a look at a more complicated connectionist model and some of the implications of that as well. But before we go, any questions about this sort of beginning idea of connectionist network? All right, so that is it for today.